Hey everyone, we're going to go through the topics for everything in chapters 9, 10, and 11. Make sure you know each of these, know how to solve problems, and use the equations for each section. So in chapter 9, we took everything we learned in 1 through 8, so motion, acceleration, forces, and translated that into rotational equations. So displacements became theta instead of x, velocities became omega instead of v, and acceleration became alpha instead of a. And we can get our kinematics equations just like we had before, with omega final equals omega initial plus alpha t, or displacement equations. So all our kinematics can be easily translated into rotating variables, but this time the object's not going to be moving anywhere, it's just going to be spinning positive or negative. And how we define positive and negative was clockwise and counterclockwise. Counterclockwise to us, use your right hand rule and rotate wherever the object is going. That's where your fingers go. Your thumb gives you a direction. If it's out of the page, it's positive. Into the page, it's negative. And we said that's also counterclockwise being positive and clockwise being negative. We then could say that we could translate all of our rotational equations into linear equations by doing a quick multiplication. If I want the linear velocity of something that is rotating, I take its rotational speed, omega, and multiply by radius. So I take radians per second, multiply by a meter, and I get meters per second, and I get the straight line velocity. I can do that for acceleration by doing alpha times r as well. We said that when things are spinning, that means they now have kinetic energy. And if they have kinetic energy, you take 1/2, instead of mv squared, we now do I omega squared. And what do we mean by I omega squared? I is the moment of inertia of the system. So you have to know what the moment of inertia is. That's really a distribution of where its mass is versus where the pivot point is. And a way to calculate moments of inertia is mr squared for point masses, or we can integrate all the mass at different locations from the axis point. That's where you get the r squared dm. And most of the time they give you the moment of inertia for whatever object we're looking at, and the way we got those different moments of inertia came from integration that people have done before. So you may be asked to do that, or you might be asked to use the parallel axis theorem, where you try to find the moment of inertia of an axis that is parallel to the center of mass and calculate the moment of inertia that way. We then got into what torque was. Torque was our equivalent of force this time. To torque something, you need to be a radius away from it and put a force on the object. The force had to be at 90 degrees, so Rf sine of theta. And we use those in Atwood problems. We saw that the Atwood is not as simple as it used to be because we always said the tensions were equal to each other. The tensions can't be equal to each other because now we're going to have the pulley actually spin. And with the pulley actually spinning, that means that each tension has to be different. So that made our Atwood problems one more step that we had to worry about and make sure that those unequal tensions torqued the pulley itself, so you had to worry about the moment of inertia of your system. So if F equals ma, then torque equals I alpha. And if you want to find something's angular acceleration, you take its net torque divided by the total moment of the object that's spinning. We also looked at torques in terms of friction, and friction causing things to roll. So there was a slip and a non-slip condition when we did the bowling ball example where the bowling ball slipped down the alley, and eventually the kinetic friction slowed the ball down enough that rotation could start, and then once you started rotating, we had non-slip conditions happening. Torque causing the ball to spin because we said that gravity was acting at the center of mass. We said that the normal force was acting parallel to the axis. So the only thing causing torque was the friction of the ground on the ball. So that's why things spin and that's why they roll. Conservation of energy was the last thing we focused on in that section, where we had objects rolling down hills and we went gravitational energy turns into linear kinetic energy and rotational kinetic energy. So since there's a spin to the ball now, we could not ignore that. This is how we had our race, and we had different things roll down the ramp to see who would get down with the fastest linear velocity, and the things that had lower moments things that were closer to the center of mass or did not need to be spun were the things that moved down the ramp as the quickest. So you have to incorporate both types of energy when things are rolling. That then led to Chapter 10. Chapter 10 was a whole section on angular momentum. And in terms of angular momentum, we wanted to look at the cross product and focus on what a torque really was. So we did a cross product of R cross F creates our torques. Remember, you've always got your XYZ plane right there on your hand. So if you have a radius along your finger, you curl your hands in the direction of the force, and your thumb tells you where the torque points. So we saw torques in clockwise and counterclockwise directions, causing angular acceleration. And since things are moving now, when things are moving, we knew from straight line momentum, you just have to do mv. We kind of do the same thing for angular momentum now. You do r cross p. You do the radius cross with the straight line momentum. And if you do some manipulation, you could just do I omega if you wanted to calculate something's spinning angular momentum. Things can be spinning and orbiting, so we have to add up all the angular momentum of a system if you want to analyze that object. We looked at torques causing changes in momentum, and torques will try to change angular momentum just like force try to change regular momentum. So there could be angular impulses with torque times time equals a change in momentum. And we also saw all those weird effects with the gyroscope. The gyroscope had a torque on it due to its own weight. It was trying to maintain angular momentum in one direction. The torque caused a change in that angular momentum, which caused the wheel to precess. Or, in third law, if I try to torque it one way, it tried to torque me back in the opposite direction. So, just like with third law, if you push on an object, it pushes you back. In third law of rotation, you torque the object, it torques you back. Which then led to the conservation of angular momentum, where we could see a spinning skater have her arms out with a very, very large moment of inertia. As they decrease the moment, they increase their spin. Colliding discs, when you had spinning discs collide together, the momentum before the collision must equal the momentum after the collision. And our favorite problem, the pivot putty. We did many different versions of that, hitting and sticking, hitting and bouncing. So make sure you can account for any way that a pivot putty problem might present itself. Remember, you conserve the energy before the collision, then you have the momentum. That's when the collision is conserved, or when the momentum is conserved, and then after the collision you have energy again. So just focus on momentum during the collision. Everything else, go for energy. Which brought us to the chapter we're in now. Chapter 11 is gravitation. And so we looked at the universal gravitation law with gmm over r squared. That's how we calculate the force of attraction between one mass and another mass that are separated by any distance, which means that everything in the universe is attracted to everything else. Kepler's laws of ellipses, and ellipses really just helps us say that law number 2, the angular momentum before and after must always be the same. That's why planets speed up when they get close to the sun and they slow down when they get far away. Or we could also look at his third law, saying that if you want to set the centripetal force equal to the universal law of gravity, you'll be able to solve for orbital velocities, or the time it takes an object to orbit another based off its distance. So Kepler was able to find the relationship of how the planets moved, and Newton was then able to use Kepler's ideas to put his laws of motion to work in them. Potential energy was a way that we could describe how much gravitational potential energy two objects have in space. Remember, we picked that 0 point as very, very far away at infinity, and as you fall towards the planet, you increase the negative amount of gravitational potential energy an object has. From that, we were able to come up with things like the escape velocity and make sure that your kinetic energy at least equals all the negative gravitational potential energy you start with on a planet. If you can match your starting negative gravitational energy with kinetic energy, you can then escape that planet if you go fast enough. So we went through derivations of how to do that, and the last unit we talked about was the gravitational field strength, or the little g, which really, by taking a force divided by any mass you put in there, gives you that gm over r squared, m being the mass of the planet and r squared being the size of the planet, the radius of that planet. Doing that, we did lots of fun examples with hollow shells and solid spheres. If you were inside the hollow shell, remember the gravity cancels out all around you. And if you're inside a solid sphere, there's no gravity at the center, but it increases and gets stronger when you get towards the surface. Once you pop out of the shell or the sphere, gravity then behaves like gmm over r squared. So good luck, study up. Tomorrow is multiple choice and free response. Good luck, do your best.